Welcome to the Continuous Delivery Podcast. My name is Zarar.
I'm Chubba.
And we are joined by a special guest today. And I know I say special guest a lot of the times, but this time it's really special because we have with us esteemed author and one of the persons who's been very influential in my thinking on how to approach software development, the author of one of the greatest books ever written, I'd say, on software development, the philosophy of software design. John Ousterhout is here. Welcome to the pod.
Hello.
Okay, so we'll get right into it because I'm sure a lot of people want to listen to your takes on these things. So, your book, A Philosophy of Software Design, is, I would characterize it as, first and foremost, a book about how to manage complexity. Because your take is that complexity is inevitable in software systems, and instead of trying to avoid it, sort of minimize it or have different approaches on dealing with it. And then in your book, you go through a bunch of approaches, which we can get into. But the first thing that I want to ask you is that you often mention that complexity, and maybe you can define that for our audience a little bit before you answer it, often grows from small decisions that a developer takes over time, and those get compounded. And eventually you get into a very complex software system. So it doesn't happen overnight, but it happens through small decisions that we make. So how do we, as a lot of developers listen to our podcast, how do you train your brain to think and observe and notice the first signs of complexity, whether it be a problematic design or what have you, that initially might seem minor, but might give you indications that this is going to get something big later on? So two-part question. One, define complexity for our users. And then what are the ways we can spot it, even when it's not massively complex, but small things that will eventually lead to complexity?
So I don't have a very crisp definition of complexity, but I tend to think of it in very broad terms as anything that makes it harder to work in a software system, either reading the existing code or trying to make changes to fix bugs or add new features. But I think there are several things that contribute to complexity, but I think the most important factors have to do with information. How much information does somebody need to have in their mind to understand this code or to go in and make changes to it? And so the less information you need to have in your mind, the easier it is to work in the code. But then there's a second factor related to information, which is if I need to know something, how easy is it for me to know that? That is, how obvious is the information? And so I think software design is a lot about first trying to reduce the amount of information people have to have in their mind at any one time. And then second, where information is needed, to try and make that information really, really obvious so I can't miss it. The worst situation of all is where, in order to understand a piece of code, or in order to fix a bug without introducing another bug, I need to be aware of some obscure line of code halfway across the system that I've never heard of. There's just no way I would ever know about this. And so short of reading every line of code in the system, I'm probably going to make a mistake when I fix this bug. That's a terrible situation. So it's mostly about that. So there are a few other factors, but I think that captures it. So now back to the point you were getting at earlier is the way I phrase it is complexity is incremental. That it isn't typically one horrible decision you made, but a whole bunch of very small things that accumulate over time and make a system complicated. So that relates to this information argument that, that each time you add a new piece of information somebody needs to learn, you're adding to complexity. And it may not seem at the time like that information is essential, is going to be essential, is going to accumulate to add complexity, but it does. So, really good question about how do I think about this in order to not let complexity accumulate. But I'm not sure I have a great answer to that. I think you just need to have a very nitpicky mindset. Mm-hmm. I think oftentimes people are aware when they're making these decisions that add complexity. It's when if you have to rationalize something in your mind, think, well, I know this isn't quite the cleanest way to do it, but I really have to get this bug fixed today. Or if I try and fix it, it's going to take this big, long, complicated process. So I'll just add it. So the first thing is catch yourself when you're rationalizing. I think people generally recognize complexity when they see it. And then the other thing is just train yourself to be very detail oriented. But in general, I think engineers are good with details. It's to be a good engineer, you have to be very detail focused. And I think engineers are capable of recognizing that details matter and that every little bit of information you force somebody to learn is adding to complexity. So you just have to be not tolerant of that. Just simply don't accept that. And when you realize, oh, I'm adding a bunch of complexity here, then stop and think, is there some other way to do this? And almost always you can find a better way to do things.
Do you see a relationship? Martin Fowler has written a lot about this topic, about refactoring, and Kent Beck always goes on about it with test-driven development. What do you see the relationship between a lack of refactoring and complexity? Because I think more and more people are sort of looking at refactoring or continuous refactoring as a way to manage complexity. Do you see any correlation or any relation between those two concepts?
Well, first of all, I agree with the idea that you have to do continuous refactoring. And the reason for that is our software systems are so complicated that there's just no way for us to get the design right up front. We can't visualize the consequences of our design decisions, how those are going to play out. And so you will make mistakes. Everybody does. I do. And my rule of thumb, when I'm designing a new class, it usually takes me 3 tries to get it right. And even then there are small issues, but never, ever do I get things right the first try. If I did, I'd probably declare victory and retire. So yes, you have to be prepared. You have to be willing to take the time to refactor. Of course, complexity interferes with that. The more complicated it is, the more tentacles something will have. And so, because one of the ways complexity manifests itself is dependencies, that this code here depends on that code over there. And so the more tentacles there are like that, the more entangled things are, then it's really hard to refactor because any refactoring affects a lot of code. Mm-hmm. So that's a problem. By the way, I will say, testing is refactoring's friend.
Right.
That is, if you have a good set of unit tests, basically unit tests give us the courage to refactor, because without unit tests, you just know there's no way you'd ever be able to test this thoroughly enough to find all the bugs. Whereas with unit tests, you can be fearless in refactoring because you can be confident that your unit tests will catch any problems you have. So the tentacles may make it hard, but the unit tests will save you and at least help you to know whether you've got it right or not.
Well, let me ask you before I go to Chaba, do you see a correlation between tested code and lower complexity code?
I wish I could say that were true, but I haven't seen any complexity. You can write tests for really complicated code.
Right.
So
true.
I don't think that would be great if there was some way that, the act of writing tests could make code cleaner. I love the idea, but I haven't yet seen evidence that that's the case.
Okay. Chaba?
Yeah. John, if you don't mind, I would like to go back a little bit to one aspect of Zarar's initial question. If you were to apply a litmus test to a code base, let's say I'm joining this company, I'm a developer, I'm joining this company, and I'm eventually have to make significant changes in this code base. What would be those litmus tests that I could apply that I would be able to tell right away, or after a very, very short time, the complexity of this system? And conversely, how would developers who work in this, that they reach that point? So let's start with the first. I don't want to give you 2 questions. So the first one is, what would those very telltale signs of a complex system or complex software?
Yeah. So I wish there was a really simple numeric metric of complexity that we could apply to systems. That would be wonderful. And people have proposed various things, cyclomatic complexity and stuff like that. And whenever I look at those, it never really feels to me like they capture the essence of what makes things complicated. So I don't know of a way to do that in a rigorous or quantitative way. I think it just boils down to, we all know complexity when we see it. Mm-hmm. I rarely have disagreement where half the people think a particular piece of code is complicated, half of people think it's really simple. I mean, the only disagreement I've seen about that is where the person who wrote it thinks it's really simple and everybody else thinks it's really complicated. And by the way, when that happens, the person who wrote it is wrong. It's complexity is in the eye of the reader, not the writer. So what can you do? Yeah, it's just as you work in the code, you start realizing how much stuff do I have to have in my mind, and how hard is it to find that information? And you see that you make mistakes, for example, because you didn't have the right information. So unfortunately, I wish I did, but I don't have a really easy way to kind of rigorously figure out whether something's complicated.
Right. So let's move to the idea of like your advice to developers on how to actually lower complexity. And one of your points that you make in the book is this idea of simple interfaces but deep modules, and how this is a sort of a protection against getting your complexity too high. Could you talk through what you mean by that concept? Because I think a lot of people might, especially maybe talk about it in a microservices context, because now we don't have simple systems anymore, unfortunately. Even the simplest of systems that does any sort of capability probably has like 2 or 3 microservices, a couple of message queues. There's a lot going on in systems now, even for basic applications that maybe in 2000 were just a monolith, and now they're distributed around 5 or 6 nodes or so on. So explain maybe the concept of deep modules and simple interfaces, and maybe try to apply it how you applied it when you first wrote the book, and maybe how that idea has changed today given the explosion in distributed systems. Does it still hold? Do we have to think about that concept differently given the new architectures that we see in the market?
All right, so let's start with what do I mean when I talk about deep classes? So this gets back to the idea of how much information you have to have in your mind when you're coding. And the best techniques for software design are those that simply eliminate complexity. This information, no one ever has to learn this information. But in large software systems, that doesn't solve all problems. There will still be a lot of complexity, a lot of things that are tricky, that may be hard to understand, can't get rid of them all. So the second best thing is we hide them so that most people, most of the time, don't have to be aware of them. Ideally, only one person, the maintainer of that module, has to be aware of it. And so that the idea is, and that, of course, that leads to the notion of abstraction. And the idea behind abstraction is we're trying to find a simple way to think about something that's actually complicated by getting ourselves to a point where we can ignore most of the details, ignore irrelevant details. So this leads to the notion of modular design and interfaces, where you take pieces of functionality, hopefully big chunks of functionality, and you encapsulate them in classes or microservices or methods within a class, at whatever level is appropriate. You encapsulate them with a very, very simple interface on top. And the interface is what someone needs to have in their mind to use this class. So that's more than just the function signatures of what's in the module. It's everything else you need to know, any sort of dependencies or ordering or constraints on arguments and so on. So the way you can think about something, how effectively have we reduced the complexity people have to be aware of, is I want to get as much functionality as possible. You can think of that as sort of complexity. And I'd like to get that with the simplest possible interface, that the least I have to learn and keep in my mind in order to access this large body of functionality. So I encourage people to think about a module, again, whether it's a method, a class, or a subsystem, in terms of these two things. How much functionality does it provide, sort of useful stuff it does? And then how much do people have to learn in order to use that? And we would like, again, the ratio of how much you have to learn to the amount of functionality to be as small as possible. And I use the analogy of a rectangle, where the interface is the top edge of the rectangle and the area of the rectangle is the functionality. And so we'd like rectangles that are very tall and very skinny, very small interface, but a lot of functionality underneath. And again, the reason for that is because that gives us leverage against complexity. We're hiding all of these details and making it accessible. People only have to learn a tiny amount instead of learning the complexities of how this thing's implemented. So to your second question, do microservices change that? I don't think so. I haven't seen anything yet that says that changes. It's the same idea. These services, they're getting more and more complicated. And so there may be more inevitable complexity that we can't hide, but ideally, you'd like to have the simplest possible interface and the most functionality behind it. I would still argue that makes sense as a design goal.
No, totally. I mean, I think where I was going more is that I think when in distributed systems now, you don't necessarily understand the consequences of your action right away anymore. I think we've gone from a more simple request response sort of style of designing systems to more request, acknowledgement, and then 8 different things happen, and then you have to figure out later how the transaction flowed through the system. So I think the point certainly still stands. I guess my question is more about we've sort of once you solve the problem of the interface complexity, now that you understand what the interface does and you can interact with it, when you actually execute a transaction, following that transaction through all the different systems with correlation IDs, I think there's a tremendous amount of complexity almost after the transaction happens that you have to manage now. And I realize your point still stands on the but I feel the architectures have introduced so much complexity that it's not just at the top. The deep modules basically isn't enough. There's a lot more going on behind the scenes that you also have to I feel manage now.
I would say that I agree with you, but I would say it a little bit differently.
Mm-hmm.
All that other stuff you're describing, to me, that's part of the interface.
Mm-hmm.
That stuff I'd have to know that I'm going to launch this thing, and then sometime later, something's going to happen, or I'll get a callback, or I'll query for a result. That's all part of the interface. So I think what you describe, what's happening is with these distributed systems, the interface has become very, very complicated. And that's problematic. The reverse of a deep class is a shallow class or a shallow module where you don't get much functionality, you get a lot of complexity.
Mm-hmm.
And so what I would say then is that a design goal for these systems should be to try and minimize sort of the number of different states that callers have to think in terms of when they're using this, or the things they have to track in their mind. I think maybe you've observed this also, but I think oftentimes what happens in a distributed system is you use this interface, but in order to debug it, you actually end up having to dive down in and see what's going on at all the levels underneath. That's
exactly my point. Is that the abstraction of you said it much better than I did, but yes, the deep class that we are hiding, you're forced to go into it more and more.
So not so deep, unfortunately. If you have to go into it,
okay,
it's not deep. Whereas, here's an example of one that is really deep and you don't have to go into it. The Unix file system, I use it as an example in the book of what I think is a really, really beautiful deep interface. It has 5 functions with enormous amounts of functionality in it, just huge. Nobody ever needs to dive in and see what order the operating system is reading blocks from the disk to debug a program that's reading and writing files. So that really, the interface really works. It really is simple. But for some reason in our distributed systems, you often do need to go in and look at all those details. And I'd say that's a problem with the design. That says to me there's somehow something that we're not effectively encapsulating, and we should be asking ourselves, is there some way we can eliminate the need for people to do this? And I will say I believe if we find a complicated problem and identify it, we can almost always fix it. I'm an optimist about that. And I think one of the reasons people become complicated, people build complex systems, is because they give up. They just decide, well, maybe it just has to be complicated, and they accept complexity. And I've noticed this in students that in the software design class I teach here at Stanford, particularly in the first project. I think people they just assume I'm building a real system that's going to be complicated. And then I point out, no, it doesn't have to be complicated. And we go through code reviews and I show them how every one of these things is complicated we can fix. And here's how to do it. And it's generally not hard to fix. So I think we just need to instill in people building distributed systems that same level of intolerance. Do not tolerate complexity. Do not assume that I'm making this a little bit complicated, but I'm sure my users will figure out how to work with it anyhow. No, don't accept that.
Nice. Okay. Csaba? You're on mute, Csaba.
It's interesting that you mentioned your students, because that's actually was my next question. I remember back my computer science days, This is mid-90s, where how we learned computer science at the time. We were given these little exercises, write these little programs, right? And the first time we encounter complexity was in real life, in the jobs of our employers. So how do you teach complexity?
Well, the only way to do it is you need to build a relatively large system. So you're getting at an important point, which I think our educational system does not really do a good job of teaching people software design. In fact, as far as I know, the course I teach is the only one in the world where the fundamental idea of software design, how do you decompose a complex problem into pieces you can solve independently, where that's a core element of the course. I don't know any other course that does that. So the way I do it in my class is that I have students build, well, I call it a complex system. You would laugh and say that's not complicated, but they build a system from scratch in the first couple of weeks of the quarter, typically a few thousand lines of code. So it's still pretty small. But even with that, there's all sorts of complexity they introduce. And then we use that and go through code reviews and show them about why this is too complicated and what they can do to make it less complicated.
So pretty much, I'm sorry.
Pardon?
No,
Yeah.
I'm sorry. Go ahead.
Yeah, so I think I would like to see our educational system doing a better job of exposing students to complexity and teaching them how to deal with it.
Mm-hmm. So pretty much what you're saying is that you follow through that year, or is it six months or a year, you take that is code and you follow through with that code base. That's what you are describing, right?
Yeah, unfortunately, it's only a 10-week quarter, which is really, really short for this kind of thing. But we do 3 phases in the class. In the first phase, students build a system from scratch. I give them no clues at all. And by the way, they all say this is the first time in their lives they've ever had to really build something from scratch. It was non-trivial with no clues about how to structure it. And by the way, they really enjoy it too. The students have a blast doing this. And then after that, we do code reviews where students read each other's code. We do reviews in class where people will present part of their project and other students will criticize it. I read every single project. It's an almost suicidal mission. I have 1 week to read 20 to 30,000 lines of code from 9 teams. And then I meet with every team individually and go over my reviews in detail. Then in the second phase of the class, they rewrite to fix all those problems. And they add some new features as well, which now exposes them to the idea of how do I modify existing code, and they make more mistakes. And we do another round of reviews after that. And then in the third phase of the class, they go back and they start from scratch with another system and build a new system with different properties, and we do a code review of that. So there are these 3 waves where in each wave they build something and they get feedback on it, and they get some opportunity to go back and revise. And I think that's where the learning comes from. That's in order to learn, you need to have the opportunity to make mistakes. Then you need to get feedback, and then you need to fix those mistakes so that you can see why fixing the mistakes really did make things a lot better.
Yeah. So what you're trying to do is like truly simulate like a real life, what would be in a commercial, like in a real life, where people would go and enhance a product. That's what you're trying to stimulate to a certain extent, I guess.
Yes, although in some ways this is even better. And I think commercially people often aren't given the time to go back and fix their mistakes because the company's in such a rush to move forward. But yeah, the idea is certainly to prepare them for that.
So as a follow-up question, so because we are both coaches, Zarar and I, and we work with development teams. And often what we find is that we got to work with developers with a whole spectrum of backgrounds. We have some who did actually formal education, computer science, and some who just did a 10-week course and then just boom, they just started coding. So they have a very varied understanding and how they deal with this complexity. What do you think is the best way to get these folks, and what would you actually recommend to our listeners? How could they increase their I don't want to say resilience, but their understanding and knowledge to deal with this complexity, while some of them been doing this for 5 years, 10 years, they are struggling. So how can they become better at this? Any suggestions, ideas?
Yeah, I do have some suggestions, but actually first I'm curious if you compare 2 groups of people, those that have had, say, an education in computer science and those that have taken short courses and learned, does the education actually help people? Do you find that group does a significantly better job than those that were self-taught in a 10-week course? I'm kind of curious.
That's actually a good question. Good question.
I myself did the formal education through the University of Toronto, and I worked with tons of teams over the years, and I have found that for most applications are fairly simple. For most CRUD applications, you can probably get away with the 10-week, 12-week course. But I think there are sometimes cases where you're especially in performance tuning, where you are writing algorithms which coordinate things across multiple systems, and you have to be more aware of basically discrete mathematics. So complex, OFN, performance, algorithm design. So I would say for 10 to 15% of cases, it does matter, but for the vast majority of cases, it doesn't really matter, because most applications don't require a high level of skill. I guess so. That's what we might take.
I see your point. If you're talking about top level application code that's doing web pages, whatever, that's pretty simple program. Yeah, it's the infrastructure stuff, I think, where that's also where the complexity issues become most important. So back to Chaba's question about how do we get people sensitized to this? So I think the most important, the first step is just to sensitize everybody to complexity. The complexity matters. It's really important. Everybody's worked in systems that were really complicated, so people know that. I think people will accept that, but you need to get people to start thinking about that, and then just ask them to think about, well, what are signs that you see that happen, that occur in complex code? How does that manifest itself? And then start thinking about, when you see complexity, how could you fix it? How could you make it be less complicated? And if you just get people thinking those basic thoughts, they may not initially latch on to the best ways to cure complexity, but that will get them thinking. And then you can start introducing ideas like deep classes and things like that people can actually apply to fix the problem. So the first thing is just talking about it. And then I think the second thing is code reviews. Get people to review your code and review other people's code, and make sure that the code reviews don't just talk about low-level issues like bugs and coding style, but whether it works, but also talk about the design issues. What's right or wrong about this code from a design standpoint? Mm-hmm. And even if the place you're at in your company, you're not going to be given time to actually fix the problems. Even if that's the case, well, don't just punt completely. Still talk about it and talk about the design so people are aware about that. And then when they have an opportunity, when they're designing something new, then they can look for trying to improve the design. And then the next step is to get management, to allocate time for actually fixing design issues.
So you alluded to a code reviews there a couple times, and Chaba and I, when we go to engagements, we often, and maybe this could be something you could experiment with at Stanford, is that we've always observed much better output from pair programming or mob programming style of working versus individual people working independently. We don't have any research paper published on this one, but have you observed in your students, or have you tried something or any experiments where when you actually do pair programming for the whole project or for the whole feature versus if you are individually working on a feature, have you noticed any differences? Are there any learnings you can share from your students? Because it's an academic setting, but I think it applies directly to the real world.
I don't have any information I can share. In my design class, the students work in teams of 2. They're welcome to do a pair program if they want, but typically they divide the task up, and one person does one chunk of the project, the other person does the other chunk. So they don't do pair programming. I haven't done pair programming myself, but I see your point about it. I think the potential advantage of it is that you have 2 minds thinking about it. And it's one of the things about, I think, complexity is it's easier to see in somebody else's code than in your own code. It's much easier to see the problems. And so you've got that second person who's not typing, who's there to criticize and to catch maybe these small mistakes that the other person is making. So I can see that it might be beneficial, but I'm not aware of any studies that show that.
Mm-hmm. And what I would like to add, and to Zerar's point about code reviews, and this is what we also experienced. This is an unfortunate state of the affairs in large companies, that code reviews, when they happen after the fact, often, to actually alluded to it, sometimes they have between the rock and a hard place, because if I go back and fix it, now I'm delaying this project. If I'm not, I'm knowingly leaving this guilt, right? And I'm leaving this issue in this code. So this is actually, this is where it was born for Zoran and I, and I'm pretty sure some other practitioners, where we try to push teams towards pair programming. But interesting, and this is the interesting thing, they are less hesitant to take that up rather than just letting it the old stack code reviews to be a more ongoing practice. So it's interesting that how this how this works in large organizations.
Yeah, I can see. I bet in many places the code review it's a hurdle you have to get over to commit.
That's right.
And you assume it's the last thing before you commit. You expect it to be a rubber stamp. And if that's the way the code review is done, you lose a lot of the value of the code review. Right. So for code reviews to be useful, it needs to be done early enough that people can make changes based on the code review. There has to be this assumption that after every code review, you're going to take time to make changes. So, if you have to commit your code on Friday, you don't want to be doing your code review on Thursday. You want to be doing it Monday or Tuesday.
We also find that we try to apply a lot of Deming's principles into software. And one of his main third one, I think, is the one about that inspection is too late. That we want to bake quality into the product right from the start, because if you don't do that, you go through the fixed defect life cycle, and that just elongates everything. So that idea of like building quality in to us, and I'd love to get your thoughts on it, is why we encourage pair programming so much, because code review is still inspection. It's not preventative in a way. I know it's before you commit or merge, but it's still later in the game than we would like. What are your thoughts on that?
Yeah, I can argue a little bit on both sides of that, so I'll do that. Mm-hmm. First, I think software is different from other domains. When you manufacture a car, you really need to get it right the first time. But code, it is just a fact that we won't get it right. So there will be changes you have to make after the fact. You can't get it right. And so I don't agree that a code review is necessarily too late. But of course, we all know that bugs are easier to fix, cheaper to fix the sooner you find them. So that's certainly true. And so that argues, if you're going to do code reviews again, you want to do them earlier rather than later. And I see your point about pair programming again, that this gives you an opportunity to catch things really, really early on. But, I think you could probably get many of the benefits of pair programming if you do code reviews right. If you write a chunk of code and get reviews of it, and then go back and rewrite. And to some degree, I think code reviews work better when you can look at a kind of a chunk of code together and see how all the pieces fit together. If you're doing a code review as you're writing that individual line of code, it may be hard to review the code. So even with pair programming, I think you probably need to, after you've built a chunk, go back and think about the whole thing and see, is this really working the way we thought? Probably not. And then go back and fix things after the fact. Mm-hmm. So I'm kind of all over the place on your question. I partly agree with you and partly don't.
Yeah, no, that's fine. It's just we've seen some good practical results, and we're wondering if we can point to some papers which might lend us some more authority than just our experiences.
I don't have any papers, but I like the way you're thinking on this. It seems reasonable to me.
Chaba, you want to go ahead?
Yeah, I wanted to ask. So continuing a little bit on this education, we promote katas, programming katas. I'm not sure, John, if you came across these or you ever used them in your teaching. What do you have any opinion about them? So there are some refactoring katas. There are some other ways that refactoring is my favorite. That actually looks at complexity and how to reduce complexity. Any thoughts on them?
I'm not sure I've heard that term. What was the term you said? A kata?
Kata. So these are programming exercises. So pretty much you get, in this particular case, you get a very convoluted and complex piece of code. They are fairly small, and then we give them a group of developers, usually a team, and they can usually solve this in about 2-3 hours. So they have to redesign by refactoring small pieces and then applying a very consecutive refactoring principles to it, and eventually some kind of a design pattern will emerge out of it when some kind of like they can apply multiple design patterns, whatever they pick and choose, but ultimately the code will be a much more simpler to modify code. So these are like super quick exercises that could be done in a fairly short amount of time.
Sounds like a great idea to me. I think, again, the way you learn is, you look at something that's bad and you fix it. So that sounds great. Yeah.
You're a mute.
The idea was that, like, in the industry, you're more often going to find yourself in a position where you have to change somebody else's code, then write fresh greenfield code.
Right.
Sort of that's the idea behind giving them a something to fix, basically, and say, how would you fix it? More than let's go write a SQL statement which returns a bunch of records.
Yep. Yeah, that makes a lot of sense.
So, but I do have a question for you. It's about interviewing. If you had to interview, and a lot of our listeners are hiring managers, they interview a lot, and there's a lot of developers on the market. You're trying to hire a developer for your company. What are some questions that you would recommend asking? What exercises, questions, what are you probing for when you are in the process of hiring a developer? What do you think are good interview questions that can tease out strong developers?
Oh, let me first tell you what I think are bad interview questions.
Okay, yeah, sure.
That's good. Awesome. Yeah.
Pretty much all of those that Google uses today.
Explain more, yeah, please. Yeah.
They basically take, like final exam questions, algorithm questions, pick some strange algorithm, ask you to code the algorithm, and then I think grade you based on how well you coded that algorithm. And these are typically algorithms that people will never see again the rest of their professional careers. And so, but they kind of get published in advance. And so the information's out of the web. So everybody studies these algorithms, and you go to Google for this test on something that just really has no bearing with what you're going to do in your future work at Google. And I've complained to friends at Google about this, and they say, yeah, we know, you're right. The problem is that we haven't been able to figure out what other questions to ask, and whatever questions we ask, they're going to get published on the web. And so everybody will know about them. So we're kind of in a difficult position. So I'd say what I like to do is try and find some not very hard programming problem, but something they have never seen before in their lives. And I'll just ask them to go to the whiteboard and start coding, but I want you to think out loud and tell me what you're doing along the way and why, what questions you're asking yourself and how you're approaching the problem. And then I'm not so much concerned with whether they get the answer right or not as what's the thought process behind it and how do they pursue it? Are they able to, honestly, often it's a matter of common sense. Are they able to eliminate things that common sense shows you right away are bad approaches? Or will they follow some sort of obviously crazy approach in solving problems? It's amazing some of the contorted solutions people will do. And then if they do that, I start asking them why they're doing that and see, can they self-correct? Can they, quickly, really, yeah, you're right, that's bad, and go off in a better way. And so to me, it's all about the thought process that people have. Now, the problem is, again, this wouldn't work for Google because whatever program, if I was Google, those questions would be out on the web and everybody would know what questions John's going to ask you and they would pre-study that, and then I'm kind of stuck. So this works much better at small scale. But somehow I think you have to put something in front of the developer that they haven't seen before.
Mm-hmm. So last question really is AI has taken over. I'm surprised how quickly it has, even in large companies that are sort of slow to move, how quickly it's integrated into the development workflow, whether it's Amazon's product or GitHub's product, or even just ChatGPT straight up copy pasting in it. How do you see how will the developer's life change in the future? Because I myself am using ChatGPT quite a bit for small tasks like, hey, write a function which does this, and you come back with it. Are we going to end up with a lot of bad programmers? Can you look into your crystal ball and see where does this industry, what is the developer's day-to-day look like? I don't know, even 5 years from now.
Well, the question you're asking is the question everybody in software is asking. And honestly, nobody has a clue what's going to happen. And I'm afraid I don't either. The thing about the large language models is they're doing things that most of us would thought computers were never going to do. If you'd asked us 5 years ago, we said, there's no way computers will ever do this. And yet they seem to be doing this pretty cool stuff. I asked my colleagues to explain, and nobody has a good explanation for why they work. They do seem to work most of the time, except when they hallucinate. And nobody seems to know why. So I just don't think there's any way to predict what's going to go on. But, I don't think we can predict where the endpoint is going to be, but we can I think we can predict a little bit the progression, that the stuff they will do best is writing small snippets of code, or kind of helping us. It's almost like better documentation, helping us to get into an area we're not familiar about. You write me a simple program to do this, and I see, that's how it works. And then I probably don't actually use that code. I actually go back and often rewrite it, but I understand now what I'm supposed to be doing. I think the thing that'll be hardest to do are the design tasks, decomposition. How do you take a complicated problem and chop it up into pieces? And particularly because the large language models are prone to hallucination. And so if there's anything imprecise about how you describe the problem, the language model is free to just go off into la la land on that and do something that was totally what you didn't expect. And so you'll still, even if it does it, you'll have to be able to come back and verify whether it makes sense or not. But I think that's the toughest. That'll be probably the last thing to happen. I don't know of any large language models that are doing that today.
Mm-hmm. Good answer, because we can't predict it either. But I just have been surprised that it's been adopted by the big conglomerates already. Usually they're like 6 years behind the latest Java version, but they've already caught up to the latest ChatGPT model. So its acceptance has been faster than how corps or big corps usually accept other similar technologies.
It is pretty amazing. You guys may not have been around when the World Wide Web first came out in the mid 1990s, but there was another kind of incredibly rapid. Everybody basically just abandoned all concerns and went whole hog after the web in those early days. And I think we're seeing the same kind of thing happen with the large language models today.
Csaba, I think you have one more.
Yeah, I just wanted to ask. So before closing, John, if you were to recommend, let's say, 2 or 3 books, beside yours, of course, to anyone in this space, like complexity, design, what would be those that you would recommend?
Well, unfortunately, there just aren't any out there that I recommend. There's a book that's a lower level book on coding practices whose title escapes me, but I've recommended. If you could flip through my Twitter feed, you probably don't have to go very far back, and it's a book I recommended there. But in terms of design, honestly, I think a lot of people have kind of gotten it wrong, and not focused on what's really important. These complexity issues. So there isn't another book out there that I would recommend.
So what book do you think?
From my own book, maybe you should ask somebody else besides me.
Let me phrase it differently. What book do you think needs to be written for developers to read?
That's a great question.
We're still here, listener. John's just thinking through this one.
Such a good question. You've completely stumped me. Because the stuff that I think is most important, I wrote about. So,
okay.
But that doesn't mean I know everything that's important. I'm sure there's stuff out there. There are things out there that I have not addressed that somebody should write a book about.
I'll offer my opinion on this one. I think I've read Martin Fowler's Refactoring book, which focuses a lot on refactoring patterns, how to take kind of crappy code and make it better. It talks about TDD. It's very practical and tactical. I think some theoretical work, or some more guiding principles on why refactoring is so important and how it can be injected into your software delivery cycle as part of a state in your cycle is important, because I think refactoring is something which is an afterthought right now. It happens sort of when we need it, when we realize that, oh my God, I've made a mess and now I got to change something. I got to go refactor. I don't think I have seen enough, and I've worked with a bunch of teams at this point I haven't seen a continuous refactoring mindset embedded in developers. And as you said, that is key to keeping complexity low. We just haven't had that. We have had some practical advice by Fowler, some good patterns, but making continuous refactoring a core central component of software development, I haven't seen anything like that out there.
That's interesting. Actually, I like that idea. I think, how do you organize a real design-aware process development process? How do you manage process? I've kind of said what you should do, or how you would attack the technical problems, but I haven't really addressed the social problems about how you organize your team, how much time you allow for cleaning up existing code versus writing new code, how you sort of embed this culture, this design-centric culture in your team. How do you and how do you make arguments that will convince managers that they really should make the investment in good software quality, that it really will pay for itself over and over and over again down the road? So something on how to do those social processes, that would be a huge contribution.
I know I said last question a couple times, but I do want to get your opinion one last time on, because we're talking about social stuff, team collaboration. Your thoughts on Agile, how it's evolved, where it is, where it's headed.
That could easily be another whole podcast, but I'll try and make a short answer. So I both like and hate Agile. So Agile has got it right in that, as I said earlier, we can't visualize the consequences of our design decisions. We will make mistakes. So you can't design a system all up front because you'll make too many mistakes. And so you need to do things incrementally, where you design a piece and implement it, evaluate it, fix it, design the next piece. So that's right. The thing I worry about with Agile is sometimes people take it to such an extreme that they never do any design. They say any design time at all is just wasted because I won't get it right. No, even though you won't get it right, you still have to do it. You have to try. And so sometimes I think Agile turns into basically debugging a system into existence without ever any design. And the epitome of that is test-driven development. Test-driven development really encourages that. Don't think about design. Write a test, then write the smallest possible amount of code to make that test pass. Then write another test, smallest amount of code to make that test pass. There's no point in there where you actually design. You're just hacking stuff into existence. So that's a perfect way to introduce complexity in lots of little pieces.
If Ken Beck was here, if Ken Beck was here, he probably would disagree with you, because actually he said that actually TDD is actually a design tool rather than a testing methodology. But that would be interesting to see.
I think of TDD as an anti-design tool.
Okay. So I really think, because you advocate for simple interfaces and deep modules, and you have to give TDD. By the way, we're both TDD fans. So you have to at least give TDD that it does force you to think of the API first, and forces you to say, okay, I want my API to be simple. So instead of writing a bunch of code, it does do API first design. So you have a higher chance of creating simpler interfaces if you're using TDD.
We may be exceeding your time here, but let me just try for another 30 seconds on this.
Okay.
I totally believe in API first design. I'm totally with you on that.
Okay.
And for example, I recommend people go through and write their header comments before they write the bodies of methods for a class. So do that. And I totally believe in unit tests. But the question is, what benefit do you get from writing the test before the code? I agree, write the API before the code. But why is writing the test, and in particular, these philosophies that you're only allowed to write enough code to pass a single test at a time? See, in order to get the design right, I think you have to think about things in larger units rather than just some tiny piece of code to pass one test.
Yes, I do agree that sometimes you can get too dogmatic, and if you follow the red-green refactor cycle, go one line of code. I think if you're an experienced developer, and I wrote about this a couple of days back, is that you can actually afford to write a bunch of line of codes and then make your test pass. Yes, if you take a very strict view of that, it does seem sort of dogmatic and over the top. But you know what? I think we've exceeded our time, and I know you have to go as well. So it's been a pleasure talking to you. Would love to have you and maybe Ken Beck do a bake-off on TDD at some point. And, that would be amazing. But John, thank you so much for joining us, and we really enjoyed it, and I'm sure our listeners will as well.
Happy to be here. Thank you for inviting me.